This video is about the augmented matrix of a linear system. For our notes, we'll understand that a linear system, which is familiar to us at this point, system of linear equations, can be translated into an augmented matrix. And so a matrix is just a structure that contains the coefficients of the system, of the equations of the system. And so if you can observe, a matrix really just looks like a box of numbers, but it actually represents a whole lot more. It's organized in a very specific way. And so we're just going to understand how you can translate from a linear system to a matrix and even back and forth. Once we understand how to get a matrix, we can do very efficient calculations and operations with a matrix, and so it's a very useful tool. To define an augmented matrix of a system, let's consider the following system. We have one of three equations. The first equation is 3x minus 2y plus z equals 5. The second equation is x plus 3y minus z equals 0. And the third equation is negative x plus 4z equals 11. So what I'd like to demonstrate is how to translate one step at a time from a linear system to an augmented matrix. And to do so, we'll look at first just the first equation in our system. That was the 3x minus 2y plus z equals 5. If you observe the coefficients of this equation, the coefficient of x is 3, the coefficient of y is negative 2, and the coefficient of z is the invisible 1 that's in front of the z. And then, of course, it's all equal to 5. If you look directly to the right at the matrix, you'll notice that those coefficients or numbers are what show up in the first row of the matrix. Notice the first row of the matrix is the numbers 3, negative 2, 1, and 5, which are in matching order from the coefficients of the equation, the first equation in this system. And that's exactly how you can create a matrix from a linear system. You're just copying the coefficients only, but in their order. So notice there are no variables in this first row of the matrix. It's only the numbers, the coefficients going across, and even the number that it's equal to. So in this case, for the first equation, it's equal to 5. That number shows up as well. Now, in some contexts, some authors will, in place of where the equal signs are, put a vertical bar just to represent, where the equal signs would be in the matrix. But that's not necessary, and not everyone utilizes that design. So you may see it, you may not. But either way, you can assume that the order in which you see the numbers in the matrix will match the order in which you see the coefficients of the terms in the linear system. You'll notice, of course, the second row matches the same thing. The coefficients would be 1, 3, negative 1, and 0, and that's exactly what you see in the second row of the matrix going all the way down. Notice, thirdly, the third equation was negative x, and then it skipped over. It seems like there was a missing y term. It skipped over it and went right to the plus 4z. So notice what happened in the matrix. When you had just the coefficients written down, there was a negative 1 for the coefficient of x, but then since the y term was missing, there's actually a 0 in the matrix where that missing y term would be. So we do have to fill in those missing terms with zeros, because really, wouldn't you call that a 0y? Or couldn't you write 0y instead of the nothing that's showing up in the equation? Well, sure. 0y is 0 and it wouldn't show up. So 0 is going to hold as the coefficient for that missing y term. And that's important to put in a matrix to hold all the places down. Of course, moving on, you have a plus 4z, and there's a 4 for that coefficient, and then equals 11, and then of course there's an 11 at the end of that row. So that's how you can translate from a system to an augmented matrix. Of course, if you understand this structure and translation, you could just as well go back and forth the other way if you were given an augmented matrix and wanted to go back into a linear system. Let's practice this with an example where we want to write the augmented matrix of the following system of equations. Our system has three linear equations, and they read as follows. X plus 2y plus z equals 1. That's our first equation. The second equation is negative 4y minus z equals 0. And the third equation is negative 2x plus z equals 5. Now, a great thing to observe right away when trying to translate a system into a matrix is whether we have any missing terms. So you'll notice in the second equation, there is not an x term. So I'm going to just kind of circle that blank to remember that that's a significant blank we have to account for. And in the third equation, there's not a y term. So I'll do the same there and just kind of highlight the fact that there's kind of a missing blank term there. That will have to translate into our matrix. And so we'll go ahead and rewrite our system as a matrix where we just use these big square brackets and then copy the coefficients of our equations down. So if I take the first equation, which was x plus 2y plus z equals 1, notice the coefficient of the x was a 1, and then we just leave a little bit of space. We don't cram all the numbers of a matrix row right next to each other. We have to leave just a little bit of space. The next coefficient was the plus 2y, so the positive 2 would be my next coefficient. Moving on, there was a plus z. Remember, the invisible coefficient there is a 1, so I'll leave a little space and then put a 1. And then there's the equal sign, and then a 1 on the other side. So I'll finish the row off with a 1 representing that last 1 on the other side of the equation. That's our first row, which aligns with the first equation in our system. We'll then move on to the second row. Notice it started with a blank x term. And remember, we have to be consistent with the fact that the first column in our matrix is going to represent all of the x terms that are aligned vertically in the first column of the system, you could say. So that means that the first term, or the first spot in the second row, is going to be a 0 because there's a blank missing term there. Moving on, though, down the row, the next term is a negative 4y, so we'll put a negative 4. Remember, that second column of our matrix would represent like all the y terms. And then moving on, we have a negative z, so really that's a negative 1 coefficient, equals 0, so then a 0 in the last spot. So that second row is going to represent the second equation in our system. Moving on to the third equation, the first coefficient for x is negative 2, so we'll put a negative 2 in the first spot for our third row in our matrix. Moving on, we have a blank y term. There's nothing there. That means we have to put a 0 for that y spot. And then, of course, for the z column in our matrix, there's a plus z, which would be a 1 coefficient, and that all equals 5. So we put a 5 in the last spot. So again, the matrix, when you look at it, looks kind of boring because there are no letters, there are no equal signs. It can be confusing if you're not carefully understanding what all the places represent. Remember, the equal signs could be represented by kind of putting a large dividing bar down the matrix, which helps just refer to where the equal signs would be, but it's not necessary and not everyone does that, so you don't have to do that. You could assume that given an augmented matrix, the last column could just represent everything to the right of the equal signs in the system.